So this is our lecture for Ohm's Law. The thing that I want to stress to you highly is that electricity has to follow rules and that are natural laws, and it will behave according to those natural laws. Electricity is a natural phenomena, and so if you understand the rules that govern electricity, then electricity will become predictable to you. And so I want to assure you of that. That's a really important thing to try to take the mystery away. The electricity is somewhat mysterious. A lot of technicians struggle with it, but I am confident that I can teach you electrical rules that we follow, and that you can understand electricity and understand it well. And one of the things that I hang my hat on in that regard is that it's confined by rules and laws. And so once you understand the rules and laws that govern electricity, then it does become predictable. It's no different than gravity. We know that if we throw a ball up, it's going to come down. If you walked up on top of a 2-story roof and you jumped off, you know you're going to fall and you're going to break your legs. And so electricity is as predictable as anything else. And so want to set up and start a few definitions for electricity. And so to start out with, we've got some definitions for electricity, and this handout is scanned as a PDF for you, and it's in Canvas, and so you can follow this handout along and make some notes for yourself on this. But electricity is just the movement of electrons. And so if you remember back to your science classes when they talked about atoms, and they said, well, in the inside of an atom is its nucleus, and in the nucleus there's protons that have a positive charge, there's neutrons that don't have a charge, and then there's electrons that orbit around it. And it kind of sets up a view that kind of looks like our solar system, that we have electrons orbiting around these different atoms. Well, in electricity, what moves is those electrons. And so electricity is a form of energy that we use to do work for us. And so the electricity is the movement of those little electrons that are surrounding all of the atoms. There's some materials that are good conductors, and insulators is another term that we have to learn. But a conductor is something that allows electricity to flow easily, and an insulator is something that resists the flow of electricity. And so the things that we have that are good conductors would be what? What do we usually use as wires and things like that? So copper is probably one that comes to mind that's a good conductor, and it's a relatively inexpensive material by comparison to some of our other conductors. And so we use copper and wires for a lot of the electrical wires that we'll use. Any of the metals typically conduct electricity. So steel and iron are conductors. Silver, aluminum, lead, gold is one of our better conductors. And so water also is another one that you should keep in mind that does conduct electricity. It just tap water in particular. The little secret, pure water does not conduct electricity. And so if you had distilled water and for that matter, then pure water doesn't conduct electricity. And so it's the minerals and the impurities in the water that actually can make water a conductor. But all of those conductors that we name, the gold, silver, copper, aluminum, steels, and cast iron, those are all good conductors. What is a bad conductor is the corrosion that builds in all of those. And so we know that steel and iron will corrode and rust, and the rust is not a good conductor, it's an insulator. That silver will tarnish and turn black, and that's not the corrosion on silver is not a good conductor. That copper will tarnish and it will turn green, like the Statue of Liberty or some old pennies that you've seen or things like that. Gold is really our best conductor, contrary to what some books will say. They say that some materials are better electrical conductors, but gold is considered our best for this reason, because it doesn't corrode. Gold's as beautiful when you pull it out of the ground as when as when we make a ring out of it or whatever. And because gold doesn't corrode or tarnish, then gold becomes one of the better conductors that we have. The insulators, we use plastics and rubber, ceramics, like porcelain or glass. Those are all insulators. Even just space between wires is an insulator, airspace. So having a gap between conductors would be considered a way of insulating them. As far as conductors go, there's a couple of rules. When we start talking about electricity, one of the things that I often stress to my students is that I care a lot more about the principles of electricity than I do the math. Any of you that maybe have had an electrical class in the past, they may have bombarded you with math for those classes. And for us in automotive, minimal amount of math is necessary. We'll do a little bit of math today, but the math kind of proves the science. And so that's kind of the value in it and the way that I utilize it. As far as fixing cars, and as that goes in the automotive industry, the principles that govern electricity are much more significant and important than any of the math. And so we don't really need to do a lot of math, and I don't intend to make you do a lot of math. So what we have, though, as a principle that I do want you to remember is that everything has resistance to electricity flowing. Even our good conductors have resistance. Our insulators have very high resistance, which prevents electricity from flowing, or opposition to electricity flowing. But everything has some opposition to electricity flowing. So as a rule, even of our wires, the longer that a wire is, or the longer our conductor is, the more resistance it has. That's little resistance in a short length stacks up the longer that you make it. So the longer a wire is, the more resistance it has. Then diameter of the wire, the bigger in diameter of the wire, the more electrons could flow through it, like lanes on a freeway, right? If I add more lanes on a freeway, I can flow more cars. And so the larger in diameter a wire is, the more electricity it can flow. And so those are some principles that you need to take to heart. It's the reason why the battery cables are huge in comparison to the lights, that the wires that operate your headlights or anything else on the car. We need a lot more electricity to go to our starter motor and to leave and to come to and from the battery. So we use a larger cable in diameter to allow for more electricity to come from the power source. And then to our individual components, we can get away with smaller wires. So larger diameter conductor is the less resistance it has. The smaller in diameter, the more it would restrict electron flow, the more resistance it has. The shorter the wire is, the less resistance it has. The longer a wire is, the more resistance it has. So the conductor length and diameter is addressed there. So in any electrical circuit, we're going to have these components in any simple circuit. And so I want to give a little bit of a definition this way, that circuit as a term, when we say the word circuit means circle. So circuit means that electricity left a place and wants to come back or circle back. And so when we say that this is a circuit, then our battery is our power source. The electricity left the power source and it circled back to it in that circuit. And so circuit means circle. But in any simple circuit, we have these three things going on. We've got a power source, we have conductors, and we've got a load. So the power source in automotive, we use batteries or alternators. Or another power source. They generate their own electricity. Alternators make electricity, and batteries make electricity. And so do ignition coils, for that matter. If you wanted to make a little note on here, battery or alternator, ignition coils on cars, they generate spark, and they make their own high voltage and so they're another power source. But power sources that we use in automotive are DC. So direct current is all batteries, like this automotive battery here. All automotive batteries are direct current or DC. And so if we were to graph the electricity that comes from a DC power source, one of the things about DC is DC stays constant. So if I graphed it, and anytime we graph something, this would be voltage. So voltage is on our vertical scale, and then along this axis is time. So voltage over time. So for a DC power source, if that battery makes 12.6 volts, then it makes 12.6 volts all the time. All right? So that would be DC. What we have coming out of our wall is alternating current. And so alternating current will change polarity. So it will sweep up and then sweep down. So I don't need that one on there. That should be in black. So what that basically means is on DC, we have dedicated power wires, we have dedicated ground wires. And so power comes from the plus side of the battery, electricity comes from there, supplies power, then we have a path back to ground over this way. And so to the minus side. So we have our conductors, a power wire and a ground wire. And so they supply the electricity to and from that electrical component. And then we have a load. So the load in the circuit is something that does work for us. All electrical loads produce either light, they produce heat, or they produce motion. And so an example of an electrical load that produces light would be a bulb. All right? An example of an electrical load that produces heat would be a resistor like this. And this happens to be a blower motor resistor. And so then an example of a component that produces motion would be things like motors, fuel pump like this, solenoids produce motion, a window motor like this one that we use to mechanically roll a window up or roll it down. The difference between a motor like this and a solenoid is a solenoid controls a passage, so it controls like a fluid passage. This is a transmission shift solenoid that would control hydraulic fluid to different pistons and clutches in an automatic transmission. And then we've got a motor that also produces motion that we could roll a window up by hand, or we could have an electric window motor that would roll the window up and down for us. And so our electrical loads, the biggest thing that I want you to understand is that our electrical loads, we've already established and mentioned that everything has resistance, right? Our conductors, we don't want to have a lot of resistance to electricity flowing. We want them to allow electricity to flow easily like they're supposed to do. And so we want it to allow those electrons to get to and from that load. Now, our loads are the intended resistance where work is done. It takes energy to do work, right? And so we fuel and feed our bodies so that we have energy to be able to do the work that we need to do. The electrons that are flowing in this circuit are the fuel for these loads and do the work for us. And so the electrical loads are the intended resistance. So a little secret is that inside every electrical load on a car is just a coil of wire. And so if you've never grabbed a bulb up and looked at it real close, then if you look inside the bulb, there's a little filament in there that is just a coil of wire. If this one, the resistor, if we look at that up close, then we can see that that resistor has coils of wire. And then if you take an electric motor apart, like this is like a wiper motor. If I take this wiper motor apart and look inside, then I see that it is just a coil of wire. If I were to take a shift solenoid apart, or any solenoid for that matter, and you look inside, it is a coil of wire. A relay, also you can see like a spool, is a coil of wire. So it has a load section in a relay. So electrical loads produce light, heat, or motion. Inside every electrical load is a really long wire that is coiled up and packed tightly. So electrical loads should have a lot of high electrical resistance, and they're the intended source of resistance where we do work to operate whatever component we're trying to operate. I want to spend a little bit of time talking about electrical theory. So there's a couple of theories that are out there that we speak to when talking about electricity and electronics. And so with electrical theory, there's two prevailing theories. There's what we use in automotive, which is referred to as conventional theory. And it's called conventional theory because it was the first understanding of electricity. And then there is electron theory. So there's two theories, conventional theory and electron theory. What we use in automotive is conventional theory. And so conventional theory says that electricity flows from positive to negative, all right? So from the plus side of the battery to the minus side. Electron theory says that that electricity flows from negative to positive, all right? So they say the exact opposite things. So I want to clarify this. So if I draw myself a little battery up here on the board, and I've got a plus side over here and a minus side over here. And I've got a little circuit that's coming out, and it's going to my bulb that's on my circuit. So conventional theory that we use on automotive so we'll use this blue for conventional theory, says that electricity flows from positive to negative. And then electron theory says that it flows from negative to positive. All right? So those two theories would appear to be in conflict with each other and say two exact opposite things. And so I'm going to rectify these two theories to you. And when I first figured this out, I thought I was like a freaking genius, right? Like, I'm like, wow, it's always bugged me. And so that's why I bring it up to you guys. I don't want, if it's confusing to you, ignore it and just focus on the truth that we use in automotive, that is electricity flows from positive to negative, all right? Now, I want to express what we're referring to. These two theories, conventional theory and electron theory, they're coming from two different standpoints. So I'm going to explain electron theory, which speaks to the chemistry, all right? So we know that in science and in physics and chemistry, that opposites attract, right? Negative attracts positive and positive attracts negative. Like charges, positive and positive repel each other, or negative and negative repel each other. So opposites attract. And so we also know that the electrons are what are flowing in the circuit. That is 100% fact. So it is true that the electrons are what are flowing in the circuit. And so if the electrons are flowing, then they're flowing from an excess point of having extra electrons on one side that can flow to a more positive point that's lacking electrons. All right? So that part I will not argue. So the science is absolutely true. Electrons flow, they have a negative charge, they're going to a more positive place that attracts them. Opposites attract. That's the science. What I will tell you is that this battery, as it's labeled on the battery itself, what is labeled on the battery as plus is the place that electrons come from, and so it actually has a negative charge. What's labeled negative is the place in a DC battery that is lacking electrons, which gives it a positive charge. So the chemistry in the battery is opposite the labeling. All right? So Since the chemistry in the battery is opposite the labeling, and this is where there is extra electrons, and that's where they come from, then now electron theory then agrees with conventional theory. Because this much I'll tell you, when you get out and you start doing your testing on these cars, you will quickly find out that the electrons in the circuit, in fact, do come from what we label the plus. So they come from the plus side. So conventional theory, when it says that it flows from positive to negative, conventional theory is speaking to the labeling on the battery. And since it was the first theory that came around, that's how all the stuff got labeled. And even in AC, alternating current, even in AC, the labeling is in line with conventional theory because it was the first theory. The science, chemistry-wise, sure, opposites attract. Electrons have a negative charge, and so they will flow from a negative place to a positive place. Fine. But on a DC battery, what's labeled plus, the chemistry on the inside is backwards. So, electron theory speaks to chemistry. Conventional theory speaks to labeling of electrical components, and they both agree on which way the electricity flows. But conventional theory speaks to labeling, electron theory speaks to chemistry. So in the case of DC that we use on cars, the labeling on the battery is opposite of the chemistry. Before I leave this conversation, one other thing that I need to express. In industrial electronics, they teach electron theory. So if you take electrical classes here at the college outside of automotive, they're going to use electron theory, and they're going to use it to teach you AC electronics. That's what they use in industrial applications, which is AC. In automotive, we use DC. And so DC systems use conventional theory. AC systems typically will speak to, in their classes at the college, electron theory. The truth is, in that regard, that's how you rectify it, all right? Conventional speaks to labeling. Electron theory speaks to chemistry. Now, the irony is, when they go to solid-state electronics, even in our electronics program here at the college, they have to switch over to using conventional theory because of the labeling issue, and they use conventional theory because all of your DC stuff is labeled according to conventional theory, and if they try to apply electron theory to it, then everything comes out backwards for some reason. All right? So DC stuff, conventional theory is what is applied to the labeling, and in the end, it's nothing to get real nutted up over or worried about. In automotive, we use conventional theory. All of our wiring diagrams, all of the diagnostic information, and our tools and equipment and everything else is all based off of conventional theory. And so that, in the end, needs to become your truth. This is not what I'm going to spend a lot of time on talking about. This is the only conversation we're having about this. And so from here on, we're going to just speak to electricity in terms of conventional theory. So I want to finish the thought on talking about polarity on electrical circuits. And so I mentioned that there's two different types of electricity, that there is AC and DC. So if we draw our graph where we have time down at the bottom and voltage. And so this is, say, 14 volts positive, and this is 14 volts negative. All right? So DC only does this. It always comes from the plus side and just stays constant. It delivers constant power all the time. And so AC switches polarity. So it will go through a circuit one way, voltage increases and then decrease back to zero, and then the electrons move through the circuit the opposite way. So we'll have a sweep of positive voltage and a sweep of positive, current and voltage. Current flows one way and then goes through the other way. So if you had a bulb, that literally means that the electricity went through the bulb this way and then went back through the bulb, switched direction, and went the other way, is what that looks like if you graph it. Now, with DC, it doesn't do that. DC, there's some components that care about polarity and other components that don't. And so there is polarity in DC because we have power and ground. And so just as an example, if I grab a speaker, and speaking of polarity, there are, in DC, we typically have polarity-wise, we have dedicated power wires and we have dedicated ground wires. And so if I hook the red power side to my red lead right here for my speaker, and then I hook my black lead to ground or black here, then if you watch the direction that this speaker pumps, you can hear it, but this speaker pumps outward. And then if I switch the polarity, so now I'm going to hook my red lead from the battery to the black lead for the speaker, and I'll hook the little red lead to the speaker to the black lead on the battery. And now if I hook that up, the speaker pumps in. So polarity will make a difference in a speaker's sound quality. So polarity does matter in terms of the speaker, and you can switch the polarity. But DC systems have dedicated power wires and dedicated ground wires because the power or the polarity from the power source on a DC system never changes. In another example, if I take this window motor here, it's got a little 2-wire pin here at the back, that if I hook my red lead to the bottom and then I touch my black lead to the top, I want you to watch which way this rotates. So I'll scoot this up a little bit so maybe we can see a little better. So I want you to watch how this rotates. So this one is rotating now counterclockwise, right? So then if I switch the polarity and now I put my red lead on top and I touch my black lead to the bottom and I switch wires down here, now it rotates the opposite direction and rotates clockwise. And so quite literally that is like roll the window up, roll the window down. So when we switch the polarity to a window motor like this, then switching that polarity is how we roll a window up and how we roll a window down. But polarity does matter, and it has to do with which wire you index power to ground, which way the current is going to flow in the circuit. And so their electricity is going to flow in that circuit. And so that's a quick little conversation on polarity. And so polarity, for DC, we have dedicated power wires, or positive, and dedicated negative, all right? And with AC, it switches polarity. Right now, the lights in this room, these fluorescent lights, they're switching polarity and cycling on and off 60 times a second. So some of you guys are like, well, my lights don't do that. Like, yeah, they do. They AC is set at a frequency to cycle on and off 50 times a second as it switches polarity. Now, the reality is that 60 times a second is faster than your naked eye can see, so they just look like they're on all the time to us. It's faster than what our eyes can pick up. But it does switch from positive to negative at a rate of 60 times a second. Sometimes when the ballast goes bad for your lights or things like that, you start to see lights flicker because that's what controls that cycle rate. So sometimes you can start to see it flicker. The next part of the conversation that I want to have is the definition now for Ohm's law. So Ohm's law, the law that governs electricity, is referred to as Ohm's law. And it's defined in terms of voltage and amperage and resistance. Those are three aspects of electricity that we use to describe different aspects of electricity and the way that it behaves and works. And so Ohm's law states that 1 volt can push 1 amp of current through 1 ohm of resistance. So we have these three aspects of electricity: voltage, amperage, and resistance. This is the way that I want you to understand this. Voltage is electrical pressure. It's what pushes electrons through a circuit. So we can define voltage as electrical pressure. I'm also okay if you want to make a note for yourself that it is electrical potential, or in the case of industrial electronics or the sciencey side, they often will describe it as electromotive force. All of those are fine. that voltage is the electrical pressure that pushes electrons through the circuit or forces them through the circuit. And it's also potential, that since it's the pressure that moves the electrons, then if we have high voltage, even if electrons aren't moving at all, we have the potential. No different than you could have water pressure at your faucet even when water isn't flowing, and so good enough on that. So voltage is electrical pressure. Since it's the one that pushes the electrons, then the higher the voltage, the more electrons it would push. The lower the voltage, the less electrons it would push. We measure it in volts. So voltage we measure in volts. The symbol for it is capital V. Then current, we measure in amps. So current is the amount of electrons that flow in a circuit, just like you can measure how much water is flowing out of your faucet in gallons or liters or whatever. So current is the measurement of how many electrons are flowing. We measure current in amps. The symbol is capital A. You'll hear me say amps, amperage, current. I'll try to stay kind of consistent for you, but I will use those terms synonymously because they are. Amperage and current are equivalent terms, amps for short. The symbol is capital A, and the amperage is the amount of electron that's flowing in a circuit. And so, or by simple definition, the flow or movement of electrons, it sounds very similar to the definition of electricity. Then resistance opposes current flow. So that's the definition that we use for resistance. The symbol for resistance is omega, which kind of looks like a little horseshoe. That's the symbol that we use for ohms. Sometimes we'll see the capital R for resistance, but the symbol for resistance is omega or ohms. And so resistance is measured in ohms. The symbol is omega. The rule of thumb for resistance is that since resistance opposes current flow, if resistance goes up, then current or amperage will go down. If resistance goes down, then current or amperage will go up. We should also have a little bit of a conversation about what affects resistance. We've already mentioned that in a circuit, as electrons leave and try to circle back to the power source that they came from, then in a circuit, if we get corrosion, then that is something that opposes the flow of electricity or is high resistance as an insulator. And so corrosion will cause high resistance and affect electrical circuits negatively. So does heat. So another little rule of thumb that I want you to commit to memory is that has a lot of application for us in automotive and in electrical testing in general, is that heat causes resistance. So that means if something gets hot, then its resistance will go up. And then the other part is resistance causes heat. And so that means that heat causes resistance. If something's hot, it will have high resistance. And then things that have high resistance will cause heat. So that means that things that have high resistance will get hot. In a really simple way, if you went out to start your car and it was click, 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 or cranking over slow, and you went out and felt your battery terminals and they were hot, then that would be an indication that there is high resistance at those battery terminals. In the same way, we said that electrical loads have high resistance and they're the intended source of resistance. That also means that the more electricity we pass through them, they will get hotter. And as they get hotter, their resistance will increase. And so it's something that we deal with, that we know is a truth of electricity, is that heat causes resistance and resistance causes heat. So want to look at the mathematical formula for Ohm's law. So the formula for Ohm's law that we will use is voltage divided, I usually, 1 volt will push 1 amp of current through 1 ohm of resistance. And so this is what it looks like when we calculate this mathematically. All right? So Mathematically, it's like this. So I generally refer to this as victory over automotive repair. The truth of it is, if I know any two of these aspects in a circuit, either voltage or amperage, voltage or resistance, or amperage or resistance, then I can calculate the third one that is unknown. The way that we do this is that this is between here and here is division. So the same on this side. And then this is multiplication. So what we're referring to there is that if voltage was unknown, then voltage equals amperage times resistance. If resistance was unknown, then resistance equals voltage divided by amperage. If amperage was unknown, then amperage equals voltage divided by resistance. So we get three different formulas out of this. And so in a really simple way, if I wanted to know the amperage of this circuit, then I know the voltage, I know the resistance. So then I would say the formula that we're going to use is that voltage divided by resistance equals amperage. So if I took my 12 volts divided by 6 ohms, that would give me 2 amps. So I'm not used to drawing on a computer like this, so I apologize for drawing like a first grader, but that would be the formula there. I'm going to bump up to this. This is the formula that we're speaking to there for, and the way that I always remember this formula is victory over automotive repair. That's the way that I always remember it, is victory over automotive repair. And from there, like we talked about, if we know any two, we can calculate the other unknown. Some of you may have seen a different formula which looks like this, which is E for electromotive force divided by I for intensity and R. So some of you, if you've ever had electrical, you may have been exposed to that formula, E, I, and R. I kind of cut it out of this, so I apologize for like the grade school writing as well. But it's hard to find one like this. But the reason why I don't like this is that none of that literally is on the meter or the test equipment that we use. V is on there for volts, A is on there for amps, and then we get the omega symbol for resistance on our meter. And so I kind of don't use this ever, E, I, and R. I always use V for volts, A for amps, R for resistance, or the omega symbol. So I want to back up and talk about and bring up a little bit more terminology for our electrical circuits. So we've established that every simple circuit has a power source, conductors, and a load. The reality is that every electrical load that you ever deal with, all that it needs in the simplest way is power, so plus side a conductor, power to it, and a path to ground. So power and ground, and that component should work. If it's a bulb or it's a motor or anything, they just need power and ground. So if they have power and ground, it should operate. If it doesn't operate, it's broke. So what we have up here is an extreme type of circuit failure. So we have circuit failures like this that are referred to as an open circuit. So it's an open circuit because of a break in the circuit. And so this represents the highest resistance you could possibly have, right? There is no higher resistance that we can have in a circuit than a circuit that's not connected at all. So this is one end of the extreme. An open circuit is a high resistance type of fault. And so it could be an open in either wire. This is showing an open on the ground side. It could be open on the power side. It could be open within the load itself, right? But any break in this circuit, we refer to terminology-wise as an open circuit. And an open circuit is on the end of the spectrum for a circuit failure that is called high resistance. Now, the other circuit failure that we would have, these circuit failures are considered shorts. So, if you consider that in a normal circuit, the electricity wants to go from power over here and get to ground, and the electricity is flowing that way. The normal intended resistance, we know that inside every load is a big coil of wire, that normally it would have to go through all of these windings of wire, all the way through, take a long path and go to ground. Now, if it can take a shortcut and go here and then jump beginning to end, that is now a shortcut or a short circuit. It's a shorter path. Instead of having to go through all of those windings, it's a shorter path to get back. So we can have a short in the load. That's what this would represent if you're making notes on your printout. This is a short in the load, and this is a short in the wiring. Two different types of short circuits. So we can have the electrical load that's shorted, or typically we refer to this as a short to ground. So a short to ground doesn't literally mean that the power wire has to come all the way back and touch the negative battery terminal. Everything metal on the car is ground. Power wires are usually insulated and protected, or any kind of dedicated wiring components that we want to make sure that we can control will have insulation on it. But generally, the negative source on the battery or the ground is anything metal. So all the metal parts on the car are a ground. So what it usually takes in a really simple way is that if I have a power wire and it sits there and rubs back and forth on something metal, if it rubs through the insulation and that power wire touches something metal, then it creates a scenario like this. And so a short to ground will usually blow fuses which protect our electrical circuits. And so we've got there's a lot of different fuses nowadays. But I've got a mega fuse like that. That's a very big fuse. This one's a 60 amp fuse. These are your standard spade fuses, which is an AMG fuse, I believe they call those. That's a 5 amp. This is another style of kind of main fuse that they'll use. And then these are little cartridge fuses, little glass cartridge. These are minis. They also have like micros and real small. Then BMW has their own little fuses. And then this, what I have up here, is another style of fuse that's called a fusible link. So this is a different type of wire. The intent for a fuse in a circuit is to protect the wiring on the car. And so a fuse is a designed weak point in the circuit, that if ever too many amps flow through the circuit or more than what it's designed for, then the fuse is designed to burn out and break so that it stops, the high current stops there and it doesn't light the wiring on fire. So when we weld with electricity, right? So electricity current flowing makes things get hot as well. And so what would happen, some of you are probably familiar with people that have had a fuse that blew on their car and they knew to check fuses, and they try to put another one in and it blew, and then they're like, well, I'll just put a bigger one. I kept putting this one in and the fuse kept blowing, so I put a bigger one in. It's never okay to put a bigger fuse because the fuse is designed to be the weak point for the wiring. And so you can put a fuse in and replace a fuse that becomes then stronger than the wiring on the car. So then what will happen is that instead of the fuse blowing, all the wiring lights on fire on the car. So you never want to reinvent the wheel and put a fuse that's bigger than what it originally had on the car. But the fuse is a designed weak point, and when you would have a short either in the load or a short to ground in the wiring like this, then you would have blown fuses. So I want to address this, that there's really only two possible electrical failures that we can possibly have, and they're on a spectrum. So we've got two possibilities, and so I'm going to try to test my drawing skills out again. So we'll see how I can do. I'll try to do a little better for you guys this time. But there's really only two possible failures or electrical faults that we can possibly have. And so if we put them on a spectrum, with normal in the middle. So this is what's normal. like trying to learn how to write all over again. So if that's normal, then if I run all the way over this way, if we say that over this way is high resistance, oh wow, I can't deal with that. So you guys got me, it's high resistance. So if on this end of the spectrum we have high resistance, I'm going to try to draw my omega symbol. There it is. So if on that end we have high resistance, then the highest resistance we can possibly have that we've already talked about would be what? An open, right? So an open circuit is the highest resistance we can possibly have. So an open circuit, so CKT is the abbreviation for circuit. So that would be the highest resistance we can possibly have. Now in terms of Ohm's law, this is what I want you to understand about that, is that for a DC system, we've already said that voltage remains constant. So as long as we have voltage, we don't have a dead battery, we expect it to remain constant. But one of the things that I want to draw your attention to is what that looks like in terms of Ohm's law is that if resistance goes up, then amperage will go down. So that's what our Ohm's law formula looks like that way for high resistance, that if resistance increases, amperage will increase. Because voltage remains relatively constant, then resistance becomes the factor, right? If resistance goes up, amperage goes down. And so that's what we would be seeing for a open circuit or high resistance failure. Then on the other end of the spectrum is low resistance. So low resistance there. And so the maximum low resistance that we can have, we refer to as a short. Drawing bigger is easier. So we refer to as a short. And so in terms of our Ohm's law formula, a short circuit, assuming voltage stays constant again, would look the opposite. That then if resistance goes down, then amperage would go up. So it is a spectrum because you can have some components that are high resistance all the way to maximum high resistance, which is an open. You can have some circuits that become lower and lower and lower resistance all the way to a direct short where we have our power wire shorted straight to ground. And so we can have partially shorted components, high resistance components all the way to the maximum end of an open circuit. But there's really only two types of faults. We have either high resistance faults or low resistance faults. Open circuits, the max end, infinite resistance, the highest resistance you can have, and then a direct short to ground. And then, just like we talked about with the loads, if with the load we've got that coil of wire on the inside, right? So if it shorts between the first and the second, then it may be shorted kind of in there, that it's just a little lower resistance. But if it shorts all the way beginning to end, then we're having it fail all the way out. And so some of you may wonder too, like, well, how does something like this get shorted, right? So, a couple of ways. They can get water in them, and then water would short them out. All right, that's one method. Then one of the other things that happens is that this winding all the way around, it's got it's got a insulator around it or insulation around it that is shielding it. But every time that this gets hit with electricity, one of the things I haven't told you yet is that when electricity flows, it creates a magnetic field. And so to be able to make this motor work, we'll explain it a little later, but we have opposing magnetic fields that fight against each other or work together. And so if the opposites are there and those magnetic fields, it attracts. If it's like charges, they repel. And so that's what makes motors rotate or things like that, is we use magnetism. And so when that motor gets hit with electricity, then you have this magnetic field and it makes it flex. And then when that magnetic field goes away, it contracts and it flexes and it contracts. Well, that creates a marginal small amount of movement. And so even though we feel like, well, these wires are wound up and they stay in the same place, when electricity is passing through them, they actually kind of move a little bit. And if you look at high-speed captures of electric motors, the weird thing of it is, I've seen one from a military video, and the weird thing about it is that the motor kind of looks like it's breathing. Super weird. So that causes the wires to chafe, and even if they have insulation on them, then eventually, just from operation, they can short out and wear through their insulation.